In this session, going to be discuss the cache memory concept and the performance as a part 3 of the Model 3 memory system as a part of the computer organization. We have discussed the in-length topic in the previous session 1 and session 2 related to the fundamental memory concepts and construction of the large memory with the dynamic and random access memory cells. Continuation of this, we have seen that there is a speed gap between the processor and the memory. The processor is a electronic device and memory is a electromechanical device. Since this the heterogeneous the speed mechanism, so there is a speed gap between these two devices. So in order to establish the synchronism between these devices, there is a one more device is essential called cache memory, which going to be the on either side. Towards the processor, it deals in terms of the burst mode, whereas in terms of the towards the memory side in terms of the block mode. So the burst mode and block mode, there is a size gap, and although processor deals in terms of the picosecond or nanosecond, whereas the memory deals in terms of the nanosecond and milliseconds, sometimes seconds also. So this speed gap will be quite the difficult task. It hinders the performance of the system, so we need to be amicably synchronize them. So that is only possible through the cache memory concept, right? So continuation of this, we'll see that the presentation flow will discuss the cache memory at the beginning and the locality of reference. The locality of the reference, so where the data or instruction are reside, that may be memory, or it may be cache, or the processor may be request the particular instruction or data. That data may be available at the memory, and also the copy of that it may be also available in the cache memory. So the locality of reference is the most important concept. Cache hit and miss occur. So the processor send information saying that this data or instruction I want. So at the very close to the processor is a cache memory. So that will be searched first, and if it is available, then we can say cache hit occur. If not occur, if it is not there in the cache, then it has to go to main memory. It is a travel to main memory. So there we have to search there. If it is there, main memory hit occur or main memory miss occur. So like this, miss and hit will be there, that indicates the presence or absence of that data. So that is a hit and miss. So in the hit case, the memory cycles will be less, where the miss case memory cycles will be more required, because he has to go to the next hierarchy of the memory, then he has to bring. So the mapping function, the processor release some address, so that address we need to be split and understand where that data is there. So why that mapping function is a mathematical model. It receives the data address from the processor, and it split it and try to search in the cache memory, main memory, secondary memory, so on. That is, if it is available in the main memory as a cache memory, it is a cache hit occur and respond that. So if not, then go to the next level secondary memory. If not, go to next level. Like that, the mapping function will be cope up. So the responsibility of the mapping function has to be bring the data or instruction which is requested by the processor wherever it may be available. It may be available in the cache or secondary memory or somewhere, right? So that is a mapping function we are going to discuss. Performance of the memory is a most important aspect, that is performance of the memory. So we can see that the performance of this memory, and also that is a interleaved of memory. So in order to achieve some the performance, that interleaved memory will be help lot by splitting that memory into several banks, right? So each banks have a port, that is a separate door for to enter those banks. So otherwise the entire amount of memory you can treat it as one bank, then the performance will be lesser compared to this interleaved memory concept. So coming to this cache memory concept, the processor is much faster than the main memory. Is a main memory. Obviously, the processor is an electronic device, right? It is a faster among all the devices in the system, whereas the main memory is comparatively slow because those are the slower. Inherently, they are slower. As a result, the processor has to spend more time waiting while instructions and data are being fetched from the main memory. So processor need time here. It spend time so to bring that instructions and data which is available in the main memory. So major hurdles towards achieving the good performance. So the bringing those things from the memory is a major hurdles for the processor, right? So it has to be wait till that arrive to the processor premises from the memory. So that maybe we don't know how much memory cycles is required, because the device which is outside the processor, which may be various device which are basically slower. Speed of main memory cannot be increased beyond the certain point. It is again inherent property characteristics of that main memory. To certain extent we can enhance by the some software mechanism. Cache memory is an architectural arrangement. It is an arrangement which is makes the main memory appears faster to the processor than it really has. So enhancement of the main memory speed, that is cache memory. So that is through the cache memory it is possible to boost the speed of the main memory. Cache memory is based on the property of the computer program known as a locality of the reference. So locality of the reference is a most important thing, that where that instructions or data reside, so where those are available. If it is available in the cache, well and good. It is not, then you have to bring from the main memory. So when you are bringing from the main memory, then you can give a copy to cache also, then main processor. So that we'll discuss. That is called protocols called write through protocol and write back protocol. So write through protocol will help us to give a copy to when the cache miss occur. Go to the secondary memory, search there. If it is available, then you have to supply to the processor. When you are supplying that processor, the same copy give it to cache memory, thinking in future the same that instructions or data processor may again ask. So in that sense, for the future plan, it is going to be give a copy to the cache memory. So then we will call it a write through policy. The processor is busy, you don't have a time, so just give a copy to the processor itself. So bypass or avoid the cache memory. So that is called write back policy. So write back policy is the very active policy, where write through policy is a lazy policy. So locality of reference analysis of program indicates many instruction in a localized area of the program. So there should be there at one place. So there, right? If it is there, then we can have that is. So locality of reference. So the programs are executed repeatedly during some time. The others access relatively less frequently. In a program, there are several set of instructions are there. There is a IO instructions. There is a computational intensive instruction. There is a memory related instruction. There is a string related instruction. There is a what is called the scientific or floating point operations. So there is a heterogeneous group of instructions are there, out of which the certain set of instructions are oftenly called by the processor. So those locality of reference is very high, so that will be oftenly called. Such instructions we can think in the future also it may ask by the processor repeatedly, so we can keep very near to the processor, or that is in the cache. So access relatively less frequently, such instructions is not necessary to keep in the cache. Only the instructions which are frequently accessed, So those instructions we can thinking that it may be required oftenly by the processor. So let it be very keep them very close to the processor, that is a cache. So these instructions may be once in a loop, nested loop, a few procedures calling each other repeatedly. So this is called a locality of the reference. So few instructions are called repeatedly. So those called locality of the reference. So there is a locality of reference. We can say temporal locality of reference and spatial locality of reference. So temporal locality of reference, the given set of instructions which are repeatedly asking, when it is asking at the some interval of time, after the some interval of time, or continuously, so that temporally locality of reference is also important. Recently executed instructions is likely to be executed again very soon, right? Such instructions want to execute very soon, so then again we such instructions we can call it as a temporal locality of reference. That is also called a spatial locality of reference. The spatial set of instructions in the sequence, in the sequence they are at the particular location. Instruction which address close to recently instructions are likely to be executed. So the address are very close to them. In the sequence of address, those instructions are available, called spatial locality of the reference. So cache memory. So we have processor is issue a read instruction. A block of word is transferred from the main memory to cache, one word at a time. That is a burst mode, right? In terms of DMA aspects, the philosophy you can exercise here. So one word at a time, that is a burst mode. So processor will be request. So the there is a main memory, and between the main memory and the processor there is a the speed matchmaker, or the speeding, what we can adjust the speed gap between this this device, that is a cache memory, will sit and establish the dialog on either side. So subsequent references to the data in this block of words are pounded in a cache. So the next instructions may be thinking that those are available in the cache, we can immediately, without making delay, we can supply to the processor. So any given time, only some blocks in the main memory are held in the cache. Which blocks in the main memory are in the cache is defined by mapping function, right? Any given time, only some blocks in the main memory are held in the cache. Which blocks in the main memory are in the cache is found by mapping function. So when cache is full, that due to this spatial and temporal locality of reference, some instruction thinking are most important. Saying so, those instructions may be requested by the processor. So without wasting the time of the processor, we can, in the quick manner, we can supply to processor. So in order to do so, every time it is quite difficult to go to the main memory and bring. So rather going there, we can save some machine cycle and access time. We can keep in a cache. So by doing so, what will happen? Basically, cache memory is a small memory. So you are thinking that in a program, several instructions are most important, and they are asking many times by the processor. In that sense, we kept in the cache. By keeping those instructions in a cache, what will happen? Sometime cache become full. Basically, it is small, and we are thinking that all instructions are important, and we kept very vicinity of the processor, that is in the cache. So what will happen? The cache definitely become full. So after becoming full, and few instructions came, and those are very important. So then we have to remove some of the blocks from the cache. So block of words needs to be transferred from the main memory. Some block of words in the cache must be replaced via replacement algorithm. When cache become full, then some of the instructions we have to pull out. So that is called replacement algorithm. Replace some of the old instructions which has time wise, so those we have to remove it and make a space for the new important instructions. So that is a cache hit we have heard. Existence of the cache is a transparent to the processor. Cache is a just is a some open bag. So it is there, whatever is there, it is known to everybody, especially processor and all other devices. The processor issues read or write request in the same manner. So if the data is in the cache is available in the cache, it is called read hit or write hit, right? So read hit, the data is obtained from the cache. So read hit occur, so we can get it from the cache. So write hit, so we want to write information. Cache has replica of that contents of the main memory, so that replica is there, then we can give it there. Contents of the cache and main memory may be updated at once. So contents of the cache and main memory may be updated at once. This is called write through protocol. What is a write through protocol? So if it is in a hit occur or miss occur, so in case of miss occur, then we have to go to the main memory, so the long distance where we obtained, so then we have to give a copy to processor. By doing so, in the meantime, so give a copy to the cache also, so that it may be useful in the future. So this protocol is called write through protocols, or we can also call it a lazy protocol, because it giving a copy to everybody, so that is called write through protocol. Update the contents of the cache and mark it is updated by the setting bit known as the dirty bit or modified bit. So whenever the data updated at the cache, so that how many versions are there, how many times they are modified. When it is modified and certain other data is not modified, then we can say that is a dirty bit, old bit, and modified one is a updated data. So like that discrimination will be there in the cache memory. So contents of the main memory are updated when this is a block is replaced. So block is replaced, this is called write back or copy back protocol. So there is a data is not available in the cache or main memory, it got the new data wherever it is available beyond that main memory or at this junction main memory. So then copy to give it to that main memory as well as a cache we can avoid here, give it copy to main memory only and processor. So the giving a copy to the cache we can postpone it. So postpone, so right now we don't have a time, so processor is very hurry, so that's why give importance to the processor, so cache may be secondary. So this is write back or copy back protocol. So compared to the write through protocol and write back protocol, so write through is giving copy to everybody, whereas write back is giving a copy to only processor. The others may be especially cache, so they will get in the due course or they will postpone to giving a copy to them. So that is called write back policy. If the data is not present in the cache, then the read miss occur, write miss occur, right? So read miss. So block of words. So block of words contain this requested word is transferred from the memory. So transferred from the memory. So after the block is transferred, the interested word is forwarded to processor, right? So the entire chunk of blocks will be there, transferred to the memory. Out of that block, only the desired word of is forwarded to the processor. So the desired word may also be forwarded to the processor as soon as it is transferred without waiting for the entire block, right? So entire necessity of sending entire block is not required. not there. So because processor is hurry, in order to send a bundle of words, only the interested word we need to be set. So transfer, this is called a load through or early restart. So load through protocol. So similar to that is a write through protocol. It is a load through protocol. So write through protocol is used and the content of the main memory are updated directly. So write through is a content of a main memory is updated directly. If write back protocol is exercised, the block containing the addressed word is first brought into the cache. The desired word is overwritten. So the desired word is overwritten to the new information. So that is a write back protocol is going to be right there. So there is a inconsistency of the cache block, because thinking the data is or instructions are important and bringing and keeping in the cache. In between certain execution happen, due to that execution, so data going to be updated. For example, in a certain computation, the result, for example, addition of two numbers. So before bringing those data, that results will be some value. After bringing and after performing addition, so results will be changes. So those results data should be consistent. If it is bringing and updating and avoiding or using write through protocol and write back protocol, so there could be a the data may be older, or some data is very old and some data may be very latest one. So this data inconsistency should not happen. So that inconsistency is a cache coherence problem. A bit called is a valid bit is provided for each block. If the block contains valid data, then the bit is set to 1. Else it is 0. So the 1 indicates the valid data. So valid bits are set to 0. It is a power just turned on. So when block is loaded into cache for first time, then V is equal to 1 valid bit. Data transfer between main memory disk occur directly avoid the cache. So when the data on the disk changes, main memory block is updated. However, the data is also resided in the cache, then V is equal to 0. What happens if the data is in the disk and main memory changes? So write back protocol is being used. So write back is a protocol. It avoids the disk cache memory, right? That will be dialogue between the processor and main memory. So in this case, data in the cache may also have changed, and it's indicated by the dirty bit. So the copies of the data cache and main memory are different. So this is called the cache coherence. So data can get a copy from the cache, either from the cache or main memory, both should be same. So if they are different, then something problem happen. Somebody have old data, somebody has not received the latest computation results. So that inconsistency will be there. So that is called coherence problem. So one option is to force write back before the main memory is updated from the disk. So write back exercise main memory is updated from the disk, or else we can exercise write through policy. Being a lazy protocol, it can give a copy to everybody, then to certain extent it may avoid cache coherence problem. So coming to this mapping function, as I said, it is a mathematical model. It will receive the address from the processor, and it will delegate to bring the data where it is available, either in the cache or main memory, so on that. Find how many blocks are placed in the cache. A simple example So cache consists of 128 blocks of 16 word each. 128 blocks of 16 word cache memory. Size of the cache is 2048 2K. So that 2K words. So main memory is addressable by 16-bit address. So that is a 64 kiloword. 16-bit is a 2 power 16 is a 64 kilobyte main memory. Main memory has 4K blocks of 16 words each. So the 64 memory you can construct with help of the 4K blocks of 16 words. So mainly three mapping functions are there. One is called direct mapping and associative mapping and set associative mapping. So there are three mapping functions are there which will be judiciously perform or supply the data which is requested by the processor. So via those cache memory it will be performed. That mapping function mainly in the literature the functions are available called associative, set associative and direct mapping policy, right? So let me discuss these policies in the subsequent discussion. At the beginning better we can discuss associative mapping policy, right? So I hope later will we appreciate that flow, right? So now I maybe flow maybe wrote direct associative, set associative. So I will start the discussion of associative mapping policy, right? So let me consider the main memory is a 4 kilobyte. Main memory is a 4 kilobyte. So how many address lines required then? 12 address lines. So 2 power 12 is a 4K. 2 power 10 is 1. 2 power 2 is a 2K. 2 power 11. 2 power 12 is a 4K. 4K main memory, right? So what is the locations? How many locations for 4K? 4096 locations, right? Each may be 16 word, so on that is. So main memory block can be placed into any cache position. So here blocks of main memory in order to provide to these two processor that may be a normal course. Along with that the same copy you can give it to cache also, thinking in the future it may require. So that philosophy we discussed in the previous slide. The same philosophy can continue now. So block main memory block can be placed into cache where in anywhere in any position of the cache if it is free. Wherever the free space are available in the cache, so there we can give a copy to them along with the copy to providing processor. So in order to perform this, let me see 4K main memory, right? So 4K main memory, so that is total 4096 blocks, right? So block 0, block 1, block 127, block 128, block 56, block 57, so on that is. So block 4096. So we have the first 128, second 128 and third 128, last 128, right? So we have 4096 total 4 kilobyte of main memory. This is a 4 kilobyte of main memory, right? So main memory blocks we can keep, that is. So cache memory is a 128. So block of cache is equal to block of main memory. So the same amount of memory will be provided. Maybe 16 words here and 16 words are for the block 0. So that is a philosophy. So the each block have a tag in order to maintain the consistency. What we discussed, that cache coherence protocol, cache coherence policy. So in order to maintain that updated value, we can put the tag also, right? So there is a tag will be there. So tag also indicates the which block, right? Tag also indicates the which blocks, that is. So we have 4096, that is a 2012. So we can put any block here, right? Any block of this 4096 blocks, we can keep any block here. So this is a 128 in order to identify this block number, but inside the block, block 127 may contains the block 250 of information. So block 1 may contains the block 0, maybe block 50th may contains the block of 4095. So that is, main memory block can be placed into any cache position, anywhere in the cache. So memory address is split it into two fields. Memory address which is sent by the processor, no? Processor sending some bundle address. So that address we need to be split here. That mapping function, that is associative mapping function, responsibility of the mapping function is to understand that memory address. So in order to understand that, it will be split into two fields. So one is called word, the other is called tag. What is a word? 4-bit will be word, that is 2 power 4 is equal to 16. So each block have 16 words. So each block have 16 words. What is a 12? 2 power 12 is a 4096. So 4K, that is a unique identification of all the location of from 0 to 4095. So that 12 bit is required, that 2 power 12. So that 0 to 4095 you can uniquely identify. So those blocks are coming over and sitting in the cache memory. So here, so any block of main memory can sit anywhere in the cache. That is one possibility, block 0 to block 0 of cache. So that is block 199 to 129 to block 1 may be also possible, or 128. So if block 1 is free, you can send a block 129. So thinking that block 129 we are sending to the processor, so along that the copy you can keep here. So the block 1 may be 120 to 127. So like that, any block of main memory can sit anywhere in the cache. So LSB 4 bits identified the word within the block. Within the block, how many words are there? 16 words are. Then which word they are interested by the processor? So only those words you can send. MSB 12 bits, the higher 12 bits are tag bits, identify the memory blocks when it is resident in the cache, reside in the cache. So it is a flexible, uses the cache space well, right? So efficiently that cache space will be utilized here. No restriction, no? Any block of main memory can place anywhere in the cache, wherever the free, right? Wherever the cache memory have free blocks, so there we can make it occupy, right? That's all. It's a very simple algorithm. So replacement algorithm can be used to replace an existing blocks in the cache when the cache is full, right? So that replacement, this may be a placement algorithm. So associative is a placing. So any block of main memory can sit anywhere in the cache, that is we can place. So if cache become full, then we can remove some of them, then we can exercise some replace algorithm, first in first out, first in last out, round robin, like several algorithm available in the literature. So using those algorithm we can replace the blocks when the cache is full. So cost is high than the direct mapping method. So we can discuss one more method in the subsequent discussion. Compared to that, the cost is higher. Cache become because of the need to search all the 128 patterns. So if the block 0 want to place here, we need to be search all the blocks. So searching amount of time is a essential here. It's required all 128. Why 128? The size of the cache is 128, right? So that finds the given block is in the cache. So the necessary place, the vacant place we need to be search for this searching is required. So after discussing this associative mapping policy, it seems to be very simple, and any block of main memory can place anywhere in the this one. So having understood this cache associative mapping function, that is especially looking after placement policy, so placing of that blocks into cache. So replacement, maybe several algorithms are available, so that may not necessary to discuss at this junction, right? Only the placement policy we can see. So another placement policy, that is a direct mapping policy, right? So same data we can take it to example, that is a 4 kilobyte of main memory is a with the help of 202 power 12, that is a 12 address lines is essential to uniquely identify the location. So that is 4096. So block J of the main memory maps to J model of 128. Block 1 it maps to the example block 4 map to 4 model of 128. So in that place we can place there of the cache 128. So 0 maps to 0, 128 maps to 1, 128 modulus of 129 maps up, 129 modulus of 128 is a 1, so 129 maps to 1, right? So 130 of model of 128 is a 130 maps to 2, so on, that is 259 map to 2, so on, that is a mapping is a modulus function. So modulus of size of the cache. So modulus of size of the cache. In this case, we have taken an example of 128. So in some other literature, they may be taken 64 or 256 or 32. That depends upon the example narrating for the proper example, that is the size of the cache. So let's see how we can organize that main memory 4096 blocks. So that is block 0 to 127. So there is a cache memory 128, 0 to 128. So there is a 128 2 power 7, 122 power 7. 7 bit is required to identify these blocks. So block 0 will go to the block 0. So you get 0 mod of 128 is 0, no? So it will go there. So block 129 is maps to 1. So that will let me complete this complete one. So block 129 mod of 129 mod of 128 is 1. So block 129 map to 1, right? So more than one memory block is mapped onto the same position in the cache. So that is a contention. So may lead to conflict. So for the cache block, even if the cache is not full, right? Even if the cache is not full, there is a possibility of do you think there is a possibility of mapping to some already available blocks? Maybe. So resolve the conflict by allowing new block to replace the old block. So resolve them by replacing the new block, leading to trivial replacement algorithm. So leading to trivial replacement algorithm. So memory address is split into three fields. Earlier in the associative mapping function, 2 fields. One is a tag and word. So here 3 fields. So that the lower bits are 4 bits, define the one of the 16 word. So 16 word in a block, in every block. So we have, that is a blocks, that is. So this main memory address will be split into the processor address will be sent to memory controller. So that will be split into tag and word offset or word in the associative mapping policy. Now direct mapping policy will be further, this tag will be split into tag and line offset, right? Tag and offset. So that will become 3 fields. So total memory address will become 3 fields, that is a tag and this group or block and the number of words in a block. So that will be 5 bit for the tag and 7 bit for the block and 4 bit for the word. So 7 bit for the block, what is that is 2 power 7, 128 blocks. So this 128 blocks we can identify with help of 7 bit. What is a 5 bit? 5 bit is a tag. 5 bit is a tag. So there is a 127 there is a first 128, second 128, third 128. Like this, we can have 35 5 we can have. So that is a 2 power 5 is a 32 groups will be there. 32 groups. We'll discuss further on the example, so you can understand easily that is. So here the direct mapping continuation, when a new block is brought into the cache, so the next 7 bits find which cache block is this to place. So brought into the cache, so 7 bits will help us to understand where we need to be keep from the 2 power 7. So that value will tell us in which blocks we have to place this. That will be splitted. So MSB 5 bits, that higher 5 bits finds which of the possible 32 blocks is currently present in the cache. So 32 blocks is currently present in the cache, that is. So these are tag bits. Simple to implement but not very flexible. Simple to implement. So this mechanism simple, but little difficult to implement as associative mapping policy in the previous discussion, right? So this is simple. Only compute the modulus, and that location will be there, and that will be once you found that location from the 2 power 7, we can able to identify and place there, right? So only this address will be split into 3 components. One is called word of the number of bytes in each block, and 7 the identify the cache block, and 5 bit is identify the group, that is a tag. So that tag will be 5 bit will be there for identification. So let we see in elaborating as an example. The same example will continue. So that is a 128 cache, that is a 7 bit. This is 7 bit. B is missing here. 4 kilobyte main memory, for which you need to be 16 bit address. 16 bit, sorry, 12 bit. That is 16 bit for 64 memory, 64 byte memory. Okay, that should be 64 byte main memory. So here we will continue the same example, that 4K, but it is 12 bit. This will make it correction 12 bit. So this 4 kilobyte memory, that is a 2 power 12 is a 4K, that is 4096. So 4096 blocks we can observe. Block 0, block 1, block 2, block 3. So as we see in the previous that vertical, so now we can see horizontal, so 29, right? So vertical you can see 0, 1, 2, 26, 27. So this is a first zeroth group. This is a first tag, that 5 bit they are referring now. So last higher 5 bits are used for the identify the tag. So the tag we can use is a what we call group. We can group 0. So is a group 1, group 2, so on. So group 2 will be 128, so 255. So first group we have 0 to 127, 7 second one, third one will be 256 to 384, right? So on third the fourth one, right? Fifth one, so on up to the 30th one. So first to 30th one, and we have 3840, 3960. So lastly we have 31, that is 31st. So 3968, 3969, 4094, 4095, right? So lastly we have, so 0 to 4096, that is 4K. So 12 bit is enough to. So this is a main memory blocks. In the previous case we have seen in the vertical. Now we are seeing in the matrix fashion, right? Matrix fashion. We can spread as a layout, that is. So it may be understandable more compared to the previous one. The main memory was in the vertical fashion we have seen. Now we are seeing in the matrix fashion. So the first 128, second 128, third 128. So like this 32 128 blocks will be there. So we have seen. So this is the this tag or group 5 bit 2 power 5, that is we have seen 3 fields are there. MSB 5 fields will be there for to understand the groups. 32 groups will be there, right? So we have the 128 blocks are there. 128 blocks is as a cache blocks. So we have a cache memory. So that cache memory is also that is a 128 cache bits. So for which we require 7 bit to identify them. So this is a cache memory and this is a entire main memory. So now understood this layout in a different way. So now we can start exercise those direct mapping algorithm. So direct mapping algorithm maps the 0th block of this 0th group can map to 0th of cache, and 128, 256, 385 like that, 3968. So modulus 128 is 0. All those blocks which are eligible in this row, which are the blocks available at this 0th row, all these are eligible to sit here in the cache block of 0, right? So what are those? 0, 128, 256, 385, so on, 3968. All these blocks are eligible to map or sit in the cache block. Other than this, none other is eligible. 129 is not eligible here because 129 modulus of 128 is not 0, that is 1, right? So that's why only the blocks which are available in this row are eligible to sit here, right? Similarly, so the 0 will maps to 0, 128, 256, 3840, 3968. 1 will receive first block, 1 will receive first block, 129, so on, 3969. Second will receive 130 and so on. Fourth will receive so on. 2 will receive, that is 2, 130, 3970. So 127 will receive this 127 cache block, able to accommodate the 127, 255, 384, 511, 3967, 4096. I hope you able to follow. The corresponding row or of blocks are eligible to sit in the corresponding row of the cache. That's all the entire philosophy behind this. So that is a direct placement policy. So direct placement policy, there is called one more called set associative mapping. So that set associative will be the same thing will be considered, and we have a cache. So we can perform this cache. So block of cache can grouped into sets. So mapping function allow to block of the main memory to inside a any block of the specific set. So address will be spread. So divide the cache into 64 sets with 2 blocks per set. Memory block 0, 64, 128, etc. map to black 0. You have seen that. So and they can be occupy either of the two positions. So in the previous associate direct placement policy, we'll have only one block, only one cache. So here we have a 2 cache. So there is one more cache will become. So that will be a set consider. This is a one set. Similarly, multi-set associative mapping policy we can have. So the modulus of that will going to be occupy that. Memory address is split into 3 fields as we seen in the previous. So 6 field will be find a set number. Higher order 6 field compared with the tag field of the 2 blocks in a set. Set associative mapping, that is a SAM blend, is a direct and associative mapping policy. This is a hybrid policy. The combination of associative and direct property will be method property will be augmented. Number of blocks per set is design parameters. So one extreme is to have all the blocks in one set, require no sets bits. So other extreme is to have one block per set, is the same as direct mapping policy. So example, we can have the set associative. The direct one we can reconsider. So the main memory and this tag and the blocks of main memory, and the set will be two. Instead of one set, we can also have multi-set. So at this section, two sets will be there. So one set and set 2, set 0 and set 1 will be there. Double the cache, so cache memory will be more. So for the same main memory. So we have that what we called mapping. Mapping will be 0, S0, that what is called set 0 and set 1 able to receive 0, 128, 3968 blocks. The map that what is called set 1 and set 2 will able to receive, these is able to receive all these blocks, which are the corresponding row blocks are able to receive in the corresponding row of the set, that is either set 0 and set 1. So we can see in the more elaborate way, set 0 of 0th position and set 1 of 0th position will able to receive 0, 128, 256, 3840, 3968. So set 1 and set 2 of 0th position. So set 1 and set 2 of 0th position will able to receive all these, right? So that is a set associative. Here that is two-way set associative. So set 0 of 1 and set 1 of 1 will able to receive 1, 129, 396 and so on, that is. Similarly, set 0 of 2 location, set 1 of second location will able to receive block set 2 of main memory, 130 of main memory, 397 of main memory able to receive, that is. Similarly, yes, set 0 of 127 and set 1 of 127 will able to receive 127, 258, 384, so on, 4095. So this is an example for set associative, that two-way set associative mapping policy. This is a hybrid mechanism, both the set and direct mapping policy is adopted. So let's consider the performance parameter of this memory system. So the key design of objective computing system is to achieve the best performance at the cheaper cost. Price performance ratio is common major success of the processor depends on how fast machine instructions can be brought into processor for execution, how fast the instruction can be executed and understand the meaning. And the one way can achieve that interleaving divides the memory system into number of memory modules. Each module has its own address buffer register and data buffer register. The simple concept is there. So entire memory you can keep it use as a entire whole memory. In order to use that, there is a single door and single exist, input and output. So that always that will call as a port. So that single port may not enough. It may be time restrictive. Access will be limited. So for that case, we can open a multiple doors. In order to open a multiple doors, better split that memory into several banks. So that is interleaving concept. So that we call it, instead of calling banks, we can call it modules. So memory will be split into several modules. Each module have their own entry and exit or the ports called through the buffer registers or data registers. Okay, let me see. Arranges addressing so that successive words in an address space are placed in a different modules. Successive words we can place in a successive location or successive module or in the same module. So we can make it, that is. So that is when request for memory access involve consecutive addresses, the access will be able to different module, right? So different module will also help us, since parallel access to this module is possible. So in the earlier entire memory you can use as a one chip or one module, then the parallel access may not be possible. So the average rate of fetching words from the main memory can be increased. So in order to increase the average access of the main memory, so we can better split that memory into modules. So that is called higher interleaved memory. So there is a two way we can do that. Is one is called higher order interleaved memory. So that higher order arrangement. So that higher order arrangement, that is, we have, there is a address generated by the CPU. So that can split into two component. The higher bits called is module and lower bits is called address in a module. So main memory will split into module address and address in a module. So that is a k bit per module, m bits per the address in a module. So this we can have, that is, so module we can have, so module have that will be what we'll call it as address buffer register, data buffer register. This is module 0. This is the first module. So first module connected to this one. Similarly, second module also n number of modules will be there. So n minus 1 modules will be there. Each modules have their own buffer registers, either address or data buffer registers. So this is the 0 module, first module. So second, higher order interleaved arrangement, right? So here, that is, so similarly lower order interleaved, that is we have higher address will be higher address in the module, lower address will be just the module number, m bits, k bits. So we have module 0, module I, so on, that is, right? So this is a module and module address in the module. So lower order addressing. So let me see how this example of higher order arrangement. So this is a 0th model, that is M0 model. So data stored, that is 0001 0110, so on, that is 1 0 1 2 3, so on, that is the consecutive words stored in a consecutive location of the same model, right? So can have, that is a 4 that is 0 1 2 1, that is, so we have, that is, so this is altogether 1 2, this is 3, and this is 4 5 6 7 8 9 10 11, right? So those words are stored in the continuous model. That is similarly 16 17, right? Sorry, 12 13 15. So that M0 to 4 models are there, and words will be stored continuously in the model. The other lower order mapping, that is, so words they spread across the several model. So 0 1 2, this is a what we call it as this is the first model, second model, third model, fourth model. So words are rather storing in a single model is spread across the all the models. So 0 1 so on, that is, right? So here that similarly 4 5 6 7 so 8 9 10 11, so that is 12 13 14 15. So here stored model wise, here store the here also model wise, but in a different model it will be stored, that is. So here that example is m is equal to 2 power m, that is 2 power 2 is equal to k models. 4 models are there, sorry, 4 models. So 2 power k, that is 2 power 4, that 16 words are there. 4 models and 16 words. The words will be stored in consecutive words available in the single model, consecutive available in the all consecutive models. Consecutive words are available in the consecutive models, that is lower ordering. Consecutive words are available in the single model, that is higher order modeling. So that we can a memory of words that is n equal to 16 with the modulus m is equal to 4, cache containing words 2 power n minus m is equal to 2 power 12, that is a 4k. 1664 with the two modules, that is, right? So that is, we have example 16-bit address will be there. There is a decoder. So model 0, model 1, model 2, so model 15. So 16 modules are there. So 64 memory split into 16 modules. So each have, that is 64 divided by 16, right? So each model have that capacity. So 16 modules are there. So hit rate and miss penalty. So hit rate and miss penalty. Hit rate should be higher for the improvement of the performance. So better performance, high hit rate should be there. Miss penalty in the sense, so there is a missing of words in the cache, so we have to go to the main memory. So the main memory is a costlier, so it need more memory cycles. In other words, more access time. So more missing, miss penalty will be more. High hit rate, the performance will be better, less number of clock cycles. Hit rate can be improved by increasing the block size while keeping the cache size constant, right? So block size you can increase. So block sizes that are neither very small nor very large. So moderate one will be yielding best result. So miss penalty can be reduced if the load through approaches is used when loading a new blocks into cache. So there is a maybe a 0 address instruct format or 1 address instruct format. So that is general purpose machines which will with help of the 1 and 0 are mostly use the load and store instruction. So load through approach is used when loading a new blocks into cache. So we can save that is high performance processor. Two levels of cache are normally used, L1 and L2, instruction and data. Average access time is a system with the two levels of cache is that is a T average is equal to H1 of C1, that is a 1 minus H1, so that is a failure miss penalty. H2 into C2 plus 1 minus H1 into 1 minus H2 into MEM. So C1 and C2 are the cache, so H1 and H2 are the hit rate of their respective cache. So using those, the formula is constructed. So that will be average access time when two levels of cache is exercised. So the other performance enhancement, write through. Each write operation involves write to. That is, if the processor has to wait for the write operation to be complete, it slow down the processor. That write through will be complete the slowdown. That is, processor does not depend on the results of the write operation. Write buffer can be included for temporary storage of write request. So processor place each write of request into buffer continuously execution. So it keep the request and continue the execution. The subsequent read request reference data which is still in the buffer, that is right. So that will be there in the data is a buffer. So we can have request reference with still, then it is data is reference in the right buffer. Right back, so block is written back to main memory when it is replaced. Block is written back into the main memory when it is written. If the processor waits for this write to complete before reading the new block, it is a slowdown. So processor waits for this completion, so it will be slowed down because of this protocols. Fast write buffer can be hold the block to written, a new block can be read first, right. Pre-fetching is a part of the performance enhancement of the system. So new data are to be bring into the processor when they are first essential. Processor has to wait before data transfer is complete. So processor has to wait in order to need that data. Prefetch the data into cache before they can actually need it. So advanced fetching up instruction is essential here in order to avoid the processor waiting time or before read miss occur. Prefetching can be performed through the software also by adding instruction called machine language of the processor. So that is a prefetching. Inclusion of the prefetch instruction increases the length of the program. So normally we can include wait operation, op operation, no operation, such as delaying instructions are introduced in order to do so. Prepatching can also be accomplished using hardware circuitry that attempts to discover patterns in memory reference and the prepatches according to this pattern. So pre-patching or the advanced patching of instruction, thinking that performance the processor may request them in order to avoid that waiting time the processor, we can supply as early as possible. So lock of free cache. So the free fetching scheme does not work if it is stop other access to the cache until the pre-fetch is completed. So in between the free fetch cache may be there, so that may be disturbed. Cache of this type is said to be locked while it is service amiss. Structure of the cache which supports the multiple outstanding misses is called lock of free cache. Multiple misses happen for which it supports the lock of free cache. Since only one miss can be serviced at a time, so lock of free cache must include circuit that keep track of all the outstanding miss. Unless the several miss happen the system, so that we can tackle in bulk. So special register may be hold the necessary information about this miss. So those are the part of the future discussion at this junction concerned to the performance of this to handle this miss penalty and increase the hit rate. So all this exercise will be taken care, right? So from this I hope understood the concepts of this cache memory and its performance. Thank you for patient listening of the cache memory and performance factors of this memory concept. And the reference books are as usual the Karl Hemacher and that is Rancic et al. Computer Organization 5th edition, Tata McGrail, William Stallings, Computer Organization and Architecture by Pearson Education, and also other books. Thanks to coordinator, moderator, subjects expert. If you have query, post to query to this mail ID. Thank you once again. Thank you one and all.